Yeah, Assalamualaikum and good afternoon again to all of you. So this is the second lecture of the second chapter for Thermodynamics, Physics for Engineers. So in this second lecture, we will be talking about the first law of thermodynamics. So by the end of this lecture, you should be able to understand and grasp the concept of internal energy, and then you are able to do calculations relating heat transfer, specific heat and latent heat, and then do the analysis with regards to the relationship between work, internal energy and heat in any thermodynamic processes. And then we will look and understand what is the first law of thermodynamics, and then look at what are the simplified models of thermodynamic processes, and then lastly we look at energy transfer mechanism, and this energy transfer mechanism is specifically for thermal energy transfer mechanism. Okay, so let's start with understanding a new concept again. So this is a new concept that we have not gone into in detail in the last lecture, which is internal energy. So what is internal energy? Internal energy is all the energy of a system that is associated with its microscopic components. So meaning to say, when you have thermal energy, okay, thermal energy is made up of the internal energy of a substance. And internal energy looks at the microscopic components of the energy of each individual atoms and molecules. The system is viewed from a reference frame at rest with respect to the center of mass of the system. So we know that microscopic energy of atoms and molecules consists of molecule translation, molecule rotation, molecule vibration, and intermolecular energy. All right. So one thing that we need to be clear about internal energy is internal energy is a relative measure. What does that mean? It means that it's very difficult for you to quantify the instantaneous internal energy of any particular system or substance. Okay, this is because internal energy must take into account all the microscopic components, right, of the individual atoms. How are you going to measure individual atoms' movement or rotation or vibration? It's very difficult. You can approximate, but it can never be accurate enough. Okay, so therefore, internal energy, we are more interested in knowing the relative measure of the energy itself. That means, what is the difference between the initial and the final state of the energy? Or basically the change in internal energy, delta E internal. Okay, so sometimes in other books or in other lecture notes, this is also denoted as delta U. Okay, U is also sometimes referred to as internal energy if you look at other books. But for our book that we use, okay, the symbol that is being used is E subscript INT. So this is the change in internal energy. So to give you an analogy similar to change in internal energy is if you look at Newton's law or mechanics of the mechanics of Newton law, you can have gravitational potential energy, right? It's very rare that you always look at the absolute potential energy. You always look at delta P, which is um, the the relative change in potential energy. So similarly here you are looking at the relative change of internal energy of a particular system when it goes from the starting of the thermodynamic process until the end of the thermodynamic process. So delta E INT is equals to the energy at the end minus the energy at the very beginning. Okay, now this is a revision of heat. So we know that heat is defined as the transfer of energy across the boundary of a system due to temperature difference between the system and its surrounding. Or if you have two different objects, okay, is the heat transfer between the two different objects is the thermal energy transferred due to temperature difference from the high temperature object to the lower temperature object. So now we need to relate between heat, internal energy, and also temperature, which are all different quantities. Okay, so be sure to use the correct definition of heat. You cannot talk about the heat of a system. You can refer to heat only when energy has been transferred as a result of a temperature difference. Okay, James Joule found out that it took approximately 4.18 joule of mechanical energy to raise the water by 1 degree Celsius. So that's how we get the unit of 1 calorie. So 1 calorie is equivalent to 4.186 joule. Okay, and it is known as the mechanical equivalent of heat. A more proper name would be the equivalence between mechanical energy and internal energy, but the historical name is well entrenched. Okay, so actually we are relating mechanical energy with internal energy. All right. Now, talking about heat, we can have what we call the specific heat or the heat capacity, capital C, of a particular sample is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. If energy Q produces a change of temperature of delta T, then Q is equal to C delta T. Specific heat, on the other hand, is the heat capacity per unit mass. So I believe most of you are familiar with this equation here. Okay, whereby small c is equivalent to Q heat over mass delta T. And ultimately, the relationship between Q and C small c is this equation here, 19.4, which is it describes the amount of heat energy that needs to be transferred in order to increase the temperature of the object by delta T, where M is the mass, C is the specific heat capacity. So this one you all are well familiar with. Okay, it's just a revision for you. So this table here shows you all the specific heat values of different elements and different material. All right, so all you need to look at is in terms of the magnitude of the number. The higher the specific heat means more heat energy is needed to increase the temperature of that particular element by 1 degree Celsius. It also means that if the element is reduced in temperature by 1 degrees, it will release that amount of heat to the surrounding or to the object that it is in contact with. All right, so for example, if you look at, let's look at something like beryllium. It has a very high specific heat. That means you have to supply a very high, very large amount of thermal energy in order to increase the temperature by 1 degree Celsius for each kilogram. Okay, compare that with something like gold, for example, which have a very low specific heat. Okay, and if you also look at iron, iron has a very not 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 very high, but relative to the other types of metals, you can see iron has quite a high specific heat, which is 400 plus. The rest will have like less than that. Okay, for example, the only thing that have more than iron is aluminium. Okay, but iron and aluminium, that is why iron and aluminium is used a lot as your what they call it, cooking pan or cooking stove or your cooking wok. Okay, we don't use iron exactly. Sometimes there are some what we call cast iron, pure iron pots and pans, but the ones that you see in your house are mostly steel or stainless steel, which is basically an alloy of iron anyway. Okay, and sometimes you can have aluminium as well. Okay, aluminium, and then sometimes coated with other types of metal to protect the food from aluminium poisoning. All right, Now, let's move on to the other kind of parameter that we need to learn, the property, which is latent heat. So we know heat, so heat is Q, right? So the symbol for heat is Q, which is the energy transferred due to temperature difference. Latent heat is something else. Okay, it is still heat transferred, but it is different from specific heat. So specific heat is the amount of heat needed to be transferred in order to increase temperature by 1 degree Celsius. Latent heat, on the other hand, is the heat energy transferred needed to change the phase of a matter. For example, from solid to liquid, and then from liquid to steam, and so on. Okay, different substances react differently to energy added or removed during a phase change from solid to liquid, and so on. This is due to their different internal molecular arrangement. The amount of energy also depends on the mass of the sample. The higher phase material is the material existing at the higher temperature. For example, in a mixture of water and ice, water is the higher phase material. The initial amount of higher phase material in a system is Mi. If an amount of energy, heat transferred Q, is required to change the phase of a sample, then L, latent heat, specific latent heat, is equivalent to Q over delta M, where delta M is the final mass minus initial mass. So let's say you have a glass containing water and ice. So let's say you have one block of ice and then you have one block of water. Okay, so the initial mass of water is Mi. And then as you heat up the glass, what will happen is that the ice will shrink because most of the ice will be changed phase from solid to liquid. So therefore you will have more water and less ice. Okay, now at the end, the mass of the water have increased because some of the ice have melted. Okay, changes phase between solid and liquid. So the quantity L is called the latent heat of the material. Latent means hidden. The value of L depends on the substance as well as the actual phase change. The energy required to change the phase is therefore equals to this equation here, 19.8, whereby Q is equals to L times delta M only. Delta M refers to the higher phase material. If the entire amount of lower phase material undergoes a phase change, the change in mass of the higher phase material is equal to the initial mass of the lower phase material. So if you have a block of ice, and then if you supply heat to it and the whole thing turns into water, liquid water, then the mass of the water is equivalent to the mass of ice. Okay. The latent heat of fusion is used when the phase change is from solid to liquid. Solid to liquid is the latent heat of fusion. Latent heat of vaporization is used when the phase change is from liquid to gas. So you know, like for example, water. Water, you have ice, water, and then liquid. So in order to change completely ice into water, you need to satisfy the latent heat of fusion. Okay, and then let's give it LF. And then in order to convert all the water into this is not liquid, steam. So to convert all the water into steam, you need to have you need to supply heat, which is the latent heat of vaporization. Let's put the LV. If energy enters the system, this will result in melting or vaporization. The amount of higher phase material will increase. Delta M and Q are always positive. All right. If energy is extracted from the system, that means if you are cooling down the material, this will result in freezing or condensation. The amount of higher phase material will decrease and delta M and Q will be negative. Okay, so these are the table 20.2 shows you all the latent heats of fusion and vaporization. So that is a different value for LF and LV. Latent heat of fusion and latent heat of vaporization. So as you can see, you need more energy in order to change from liquid to steam compared to from solid to liquid. Okay. Now, before we go further, I would like to talk a little bit more about latent heat, right? So here we see that what it means, latent means hidden, but why is it called hidden? Why does it call hidden, right? So I will try to explain this to you so it makes sense. Okay. Now, let's look at the relationship between uh, temperature, right? So versus temperature versus uh, Q, heat. So you know that at temperature of 0 degrees Celsius, so if you at um okay, so if you I don't think this is correct. Yeah, it's okay. I think I can just explain. So 0 degrees. So let's say you have ice. So you have a block of ice, and then you supply heat into it. You transfer heat into it. So as you supply heat into the ice, temperature will. Okay, let's start from negative. In fact, okay. So let's say initially the ice have a temperature of minus 10 degrees Celsius, for example. So as you supply Q, okay, the temperature will start to increase. Okay, it will start to increase until it reach 0 degrees Celsius here. When it reaches 0 degrees Celsius, that is the melting temperature of ice, right? So ice will start to change phase into water. So what will happen starting at 0 degrees Celsius, some of the ice will start to sweat, so it will be converted into liquid. So as it does so, you will keep on supplying increasing amount of Q. You supply Q, but the temperature will remain at 0 because at the phase change temperature 0 degrees Celsius, the water and ice mixture will have a temperature of 0 degrees Celsius. As long as there is ice, the temperature of the water and ice will be 0 degrees Celsius. So what happens to the extra Q that you supply? Why must the temperature remains the same? This is because the extra Q that you supply, the extra heat that you are transferring into this system, mixture between water and ice, is now being used to slowly changing the phase of ice into water completely. Okay, so it will be constant here until you reach a point where all of the ice have been converted into water, roughly maybe around 4 degrees 5 degrees, it doesn't matter, but okay. Okay, so it will at any temperature that is, sometimes it's still at 0 degrees, sometimes it's 4 degrees, but then only it will. So sorry, let me rephrase that. It will not, the temperature will not change, right? So the temperature will not change until all of the ice have been converted into water. Then only the temperature will start to increase again. So sorry, yeah. So the moment at which all the ice have been converted into water, that is actually still at 0 degrees Celsius. Starting when the last drop of ice have been converted into water, then only temperature will rise again. Okay, it will rise again until you reach the temperature of 100 degrees Celsius. Okay, then this is when the water will start to be converted into steam. Okay, here the temperature will cease to increase. The temperature will remain at 100 degrees Celsius. It will remain so until the right amount of heat have been transferred into the system, whereby all of the water have been vaporized into steam. Then only the temperature will rise again. So the word latent hidden comes from how the temperature is actually not changing during the phase changes here. Okay, you are supplying more and more heat, but there's no change in temperature. So it appears that the extra energy that you are supplying is hidden somewhere. It's like you don't see it. But you can see the system itself is changing phase, the substance of the system. Okay, so that is what is actually going on. So during the changing in phase, temperature will remain constant. Ice converted to water, it will remain at 0 degrees Celsius until all the ice have been converted to water. Then only temperature will increase again. Okay, and then similarly, as you reach 100 degrees Celsius, the temperature will be constant at 100 until all of the water have been converted into steam. Then only it will increase again, the temperature of the steam. Okay, so that's what I'm trying to explain to you. Now, moving on, let's look at heat and work, how they are related. So you have looked at E internal, so internal energy, delta E INT. Now there's heat Q and W. So thermal energy can be transferred around a system or between two or more systems in the form of heat or work. So that is an important concept. So thermal energy can be transferred around a system or between two or more systems in the form of heat transfer due to temperature difference, or in terms of work. Work, that means if the gas is expanding or contracting, it can push against the boundary. If you are pushing the boundary and change the boundary of your system, then that means your thermal energy have been converted into work, mechanical work. So how do we know if the transfer of thermal energy is due to heat or due to work? So this is how we know. It is due to heat when there is a temperature difference, and then all other forms are work. So if you look at your system, if you have a temperature gradient or temperature difference, so definitely the transfer of thermal energy is due to heat. If any other kind of heat transfer is any other kind of energy transfer is happening or process is happening, then it must be due to work. Especially work is when you have to push your boundary, okay, the boundary of your system, and the boundary of your system changes. If your boundary of your system does not change, then that means there's no work done. So the work normally related to the physical interaction between the material or the substance, okay, solid, liquid or gas, and the system's boundary or wall. For example, gas valve pushing the piston in a steam engine. Okay, that's how you convert thermal into mechanical work. So for internal energy, heat and work, the sign of the value is important, meaning the positive or negative sign is important. For heat, Q is positive is if and positive Q is heat added to a system. So if you are heating up your substrate or your system, that means the Q will become plus. You are adding Q. If you are cooling it down, if heat is transferred into the surrounding from the substance, then it is negative delta, minus Q. Work, on the other hand, work is done on the system. So what does it mean by work done on the system? Let's take an example. You have a piston. If you push down the piston to compress the gas, that means you are doing work. So work is being done on the system. That means all the work that you have done is transferred into the system. Therefore, the system will have increased in internal energy. Therefore, the work is plus W. Okay, and then W is negative if work is done by the system. So if you heat up the system, okay, you increase the temperature, and then the gas inside the piston, for example, will expand, and then it will push the piston out. So the system itself is doing work in pushing the piston. That means some energy is lost by the system. So therefore, W is negative in that case. So it's very important that you grasp the idea and identify when does Q and W is positive or negative. Very, very important. Okay, so let me repeat myself. If heat is added into the system, Q is plus, Q is positive. If the system loses energy due to heat transfer, that means Q is negative. Work, if you are doing work on the system from outside in compression, that means W is positive. And if the system itself is expanding or doing work in pushing the boundary, that means W is negative. So I have written here compression and expansion to help you remember, because all compression process must involve plus W, and all expansion process must involve negative work. So work must always be done on the system in compressing it, and work must be done by the system for expanding it. So let's look at some the model or description equation to look at how do we calculate work done. Okay, so here an example of work done during volume change. Say a gas in cylinder is acting on a piston by applying a pressure P on piston surface area A, moving it a small distance dx. Then the work done by the gas or by the system is given by this. So imagine you have a piston that looks like this. You have the piston, the yellow color piston, and then imagine inside the column of the piston there is a gas, and then if you heat it up, the gas will be expanding. So when the gas expands, it will push the boundary. So which boundary can move? The piston will be moved. So the piston will move by the amount of delta X. Therefore, dW, the work done, is equals to minus F dx. F is the force that is applied, okay, whereby it is equals to pressure plus, equals to negative P pressure times A area of the piston, surface area of the piston, times dx, which is the distance that it moves. However, we know that A times dx is equals to dV, whereby dV is the change in volume. A times the area of the piston times the dx is basically the volume, so it's the same. So therefore, delta W, the change in work done, is equals to minus pressure dV. For a finite change of volume from V1 to V2, therefore, we can have a general equation whereby work done is equals to negative of the integration of pressure with respect to the volume, from the final volume to the second volume, the final volume to the initial volume. So it's given by this equation here. So all you need to know when you want to calculate the work done on the system or by the system is to know how does the pressure change with volume. Okay. So work done is area under process path for on a PV diagram. So as I mentioned, you need to know how does the pressure changes with volume. That's how you can get work done, right? So the state of the gas at each step can be plotted on a graph called a PV diagram. This allows us to visualize the process through which the gas is progressing. The curve is called the path. So if you look at the graph here, down here, you have P versus V. Okay, so this is what we call our PV diagram, PV curve. Okay, so we are trying to look at how does the pressure change with volume. So in this particular graph, okay, you need to identify a few things. One is the initial state, Secondly is the final state. So the initial state is denoted by I, and then the final state is denoted by F. So in a process, we need to know the initial state, the final state, and then the third thing that we need to know is the path. The path is this red line. So it's the line at which the system follows in order to move from the initial state to the final state. Okay, so there are these three things is very important when you are analyzing PV diagram, which is what is the initial state, the initial dot, the final state, the final dot, and then the line itself. What is the shape of the line and what is the direction of the line? That's why we have an arrow here. Now to calculate the work done based on the equation that we have looked just now, okay, this integration is actually just the calculation of the area under the curve, PV curve. So the area under the curve is actually the work done. Okay, so that's how you calculate. So if you use the equation, effectively you are calculating the area under this PV curve, right? Now let's look closely in terms of the path between thermodynamic states. The process of going from initial to final state through intermediate pathway. So there's three things just now, right? So what is the initial state, what is the final state, and what's the pathway? So let's look at these three different PV diagrams, okay, A, B, and C. So in A, you can see, in fact, in A, B, and C, all the initial and final states are the same because it is at the same volume, Vi, and at the same Pi for all three. Okay, and then the final state also for the three are all the same. The only thing different is the pathway at which the system go through in order to move from the state I to state F. So in A, it goes from here to here and then it goes up. So it goes through a constant pressure process followed by a constant volume process. In B, it goes through a constant volume process first and then only going to a constant pressure process. In the third one, in C, it goes through an arbitrary line curve like this between I and F. Okay, so all of them are compression, but the compression consists of different thermodynamic processes. So one implication of different pathway or different process, thermodynamic process, in order to move or change between initial and final state is that the work done is not the same. We have established that the work done is calculated by looking at the area under the curve, right? So if you look at A, B, and C, they are the same initial and final states, but the process pathway is not the same. Therefore, the work done, area under graph for each one of them are not the same. So looking at them in one glance, we know that in figure A, it consists the less change in work done because it's the smallest area. The most work done is for process B, whereby you have the largest area, and then the middle one is C, which is basically like a triangle plus a rectangle. Okay, so work done are different between two processes. The work done by the system depends not only on the initial and the final state, so not only on the initial and the final states, but also on the intermediate states or the pathway. So pathway of your PV diagram is actually describing the type of thermodynamic process. Okay, so we know in order to change the thermodynamic state from initial to final, there can be more than one process that you can use to achieve that. And depending on the type of process that you choose, the work done will be different. In fact, the Q also, the heat transfer also will be different as well. And the the change in internal energy also will be different. So now let's look closely on heat and work in thermodynamic processes. So let's look at one example of a thermodynamic process, which is called a closed loop process or cyclic process. A closed loop process or a cyclic process is when you have a process whereby the initial and final states are the same, where the process path forms a closed loop. The internal energy must be zero since it is a state variable. If delta, so if the change in internal energy is equals to zero, therefore Q must be equals to minus W. Okay, in a cyclic process, the net work done on the system per cycle equals to the area enclosed by the path representing the process on a PV diagram. So what does a closed loop process look like? Okay, it can look like any one of these three. Okay, so let's consider A to be the initial state, and then it goes from A to B. Okay, A to B, and then B to C, and then C to D, and then D back to A again. So therefore, this is when we have the initial state and final state to be the same, because A is the both the initial and the final state of that system, of the process of the system. Okay, and the process go through different pathway. The first pathway is A B, and then the second pathway B to C, third pathway is C to D, and the fourth pathway is D to A. And this is the same for the three processes example PV diagram here. Okay, so in a closed loop process, one thing that you need to bear in mind is that the change in internal energy is always equals to zero. Why? Because there is no change in the state. The state remains the same. From initial, it goes through the whole pathway and then back to its original state. So there's no difference between the final and initial state. Therefore, internal energy remains the same. Okay, it changes throughout the process, but it goes back to its original state. So that's for always closed loop process, in change in internal energy is equals to zero. Therefore, we can say since change in internal energy is equals to zero, therefore Q heat transferred is equals to negative work done. And the work done can be calculated by calculating or measuring the area inside the loop itself, which makes sense. Okay, because actually you need to find the work done by each pathway. But once you do that, you will come into a conclusion that the work done is actually the area enclosed by the closed loop. Okay, so understanding that give rise to the first law of thermodynamics. So if the zeroth law of thermodynamics is concerned with the definition of thermal equilibrium, then the first law of thermodynamics is concerning the conservation. Hold on. Okay, so the first law of thermodynamics is concerned with the conservation of thermal energy. Okay, and the conservation of thermal energy can be in the form of heat transferred, in change in internal energy, and then work done. Okay, so the first law of thermodynamics is special case of law of conservation of energy. It is a special case when only the internal energy changes and the only energy transfer are by heat or by work. So the first law of thermodynamics states that Q is equals to change of internal energy minus work. All quantities must have the same units of measure of energy. If all joule, then all must be joule. Okay. One consequence of the first law is that there must exist some quantity known as internal energy, which is determined by the state of the system. The internal energy is therefore a state variable. So we can rewrite equation 19.a into this equation here. So this is your equation that governs equation. So this is the equation that governs the first law of thermodynamics. So when you see first law of thermodynamics, the first thing that comes to your mind must be it's the equation relating heat transfer, change of internal energy, and work done. Okay, so delta U, so you can rewrite 19A as delta E INT delta E int is equals to Q plus W. So just remember one form. So if you remember this form, then just remember this form. And then by algebra, you can rearrange it and get to find the value of QW or delta or the change of internal energy delta E. Okay. All right. So basically, the first law of thermodynamics can be described in just this one slide. Okay, it's the equation that describe the conservation of thermal energy inside a thermodynamic system. Okay, now let's look at some of the standard thermodynamic processes, or I should say approximate model of typical thermodynamic process. Approximation. Okay, it's approximation. Why I say approximation? Because most thermodynamic processes happens very fast. Like example, if you look inside your car, the engine, the internal combustion engine, it is going through the cycle very fast, right? So it's very difficult to actually plot the PV diagram and so on. So we need to have some sort of approximation to describe complex thermodynamic processes and make it more easy for us to analyze. And for this particular course, the ideal thermodynamic processes that we need to be acquainted with are these four, which is firstly isovolumetric process, A, which is constant volume. So as you can see, if you look at the PV diagram, all right, it's a constant volume. So A has a constant volume. Why? How do I know it's constant volume? Because if you try to find the work done is zero, because you cannot find the area under the line that goes vertically like this on A. So it's a constant volume process, isovolumetric process. The second one is adiabatic process. In an adiabatic process, there is no heat transfer, so that's the condition. Isothermal process. An isothermal process is whereby the process is happening at a constant temperature. And then lastly, you have isobaric process, which is a process happening at a constant pressure. So A, this is the line. B, adiabatic process is this line here. C, isothermal process is C, and then D is a constant pressure process. It's the horizontal line. So A and D is straightforward. Okay, A and D, constant volume or constant pressure. But how about isothermal and isobaric? How do you differentiate between these two? Okay, so it lies in the blue line. So you have the red lines, which is the pathway of your process. Now the blue line is referred to as isotherms. Okay, isotherms are basically the point on the line at which, if you look at the point along the line, is anything along the line is happening at a constant temperature T1. So if you have states along the blue line, everything that is along the blue line has a constant temperature. So that's why it's called isotherms. Iso means does not change, one, so temperature does not change. So along the blue line, temperature does not change. So if your process pathway is following the blue line exactly, all right, from initial to final, that means it is an isothermal process whereby the process is happening at a constant temperature. Okay, adiabatic process, on the other hand, it follows a curve which is very what we call random. So it can be a curve that looks like isothermal process, but it changes temperature. Okay, it changes temperature. The only thing that is important for you to remember about adiabatic process is that, so not adiabatic process is that no heat transfer. Okay, adiabatic process, no heat transfer. The condition, isothermal process, constant temperature. Isobaric, constant pressure. Isovolumetric, constant volume. So let's look at them one by one, okay, to understand how does each process obey the first law of thermodynamics. So the first one, isovolumetric process. In isovolumetric process, constant volume, okay, constant volume process. Sometimes it is also called isochoric. So if you plot the PV diagram of isovolumetric process, so I think I have to move this. after this. Okay, so this is the line, okay, the pathway from initial to final, constant volume process, no work done by the system or on the system, because if you try to calculate it, okay, a straight line vertical like this, you integrate it, the result is 0. So that's why W is 0. So when W is 0, when you fit it inside the first law of thermodynamics, so first law of thermodynamics states that delta E I and T in change in internal energy is equals to Q plus W. So if W is 0, that means change of internal energy is equals to the heat transfer. So you have this. All right. All added heat remain in the system and increases the internal energy. Pressure will usually increase too. All right. Now the second one is adiabatic process. So in adiabatic process, we know that the condition is no heat transfer. So when there is no heat transfer, automatically you know, okay, for adiabatic, Q must be equals to 0 straight away. So if it's described to you, this system is undergoing adiabatic process, straight away you know, okay, Q is 0. Okay, when Q is 0, uh, then that means internal energy is equals to work done. Adiabatic expansion, W is negative, so okay, so for adiabatic expansion, W will be negative. You know, when it expands, it loses energy, so W will be negative. So delta, the change in internal energy must be negative as well. Conversely, if you are compressing it, you are doing work into it, therefore the internal energy will be increased and it will be positive. So in most adiabatic compression, the temperature will increase. So here it shows you the PV diagram of an adiabatic process. As you can see, the shape is similar to an isothermal process. The only difference is that it doesn't follow the pathway of an isotherm. Okay, it will change temperature as well. So the third one is the isothermal process. So again, the condition for an isothermal process is that the process is happening at a constant temperature. So when temperature is constant, okay, heat flow in and out of the system must be slow enough that thermal equilibrium is maintained. So that is the secondary condition for an isothermal to happen, is that the process must be a very, very slow process whereby the temperature does not change. Although when you add in a lot of extra heat transfer into the system, it must be added slowly, in such a way that the temperature is maintained to be the same. Right? So change in internal energy is equals to 0, but W and Q are non-zero. So why is the change in internal energy is equals to 0? Because temperature remains the same. When temperature same, internal energy also same from final and initial, because you know that internal energy is with regards to the vibration of atoms and the movement of atoms, and that is also reflective of the temperature. The higher the if you have an increase in internal energy, you have an increase in temperature. If you have a reduce in internal energy, you have a reduce in temperature. So if the temperature is constant, then there will be no change in internal energy. So therefore, change in internal energy is equals to 0. W and Q can have any value. Okay, at any energy that enters the system by heat must leave the system by work. So anything that goes in, so if you compress it, it will if you compress it, then the energy must be entering it by heat as well. So here we can apply this equation for finding finding W, and then you can relate it to the ideal gas law, the ideal gas equation. All right. So if you look at this, okay, you can substitute P with the ideal gas equation. You expand it, you get this, and then this can describe these two equation, which is important, right? These two equation. since for isothermal process, this relationship also you must remember. Okay, so make sure you remember all this. This can be very useful for you to answer questions regarding isothermal process. Now lastly is isobaric process. You know that isobaric is when the pressure is constant, so therefore all of the parameters inside the first law of thermodynamics equation can change. So you have the relationship to remain the same, which is Q plus W. All right. So this one are all non-zeros. Okay. The only condition is that the pressure must always be the same. So when you plot the PV diagram, it must be a horizontal line like this. Therefore, the work done is very straightforward, which is a rectangle. You can calculate that straight away without doing the actual integration. Now let's look at internal energy of an ideal gas. Okay, so we know what is internal energy. So let's look at how does the internal energy of an ideal gas behave? So we have concluded that internal energy depends only on temperature and not on pressure or volume. So that is the conclusion that we have come to. Okay, so how do we prove this theory, or how do we prove this conclusion? Is by doing some sort of experiment. So the first experiment is a free expansion experiment number 1. So in this experiment, we have an apparatus that looks like this. So consider you have a flask containing air trapped in by a piston like this, and then the flask is put on a heat plate, okay, whereby you supply heat into the flask, but very slowly in such that the process that is happening inside the system is an isothermal process. So you supply heat a little bit, okay, you transfer heat a little bit, and then that heat is converted 100% into work. How does it convert into work? It is converted into work in pushing the piston up a little bit. So therefore the internal energy remains the same, temperature remains the same. It is an isothermal process. You add heat a little bit, that heat is used and conserved into pushing the piston up a little bit by doing work. And you keep on repeating that, supplying a little bit of heat, pushing a little bit up until you have the gas being expanded to fill 5 liter. So the mass still does not change because there's no way the mass can enter in and out because of the piston, right? So the gas itself has expanded. So let the gas expand slowly by supplying heat so the temperature remains constant at 300 Kelvin, which is roughly around room temperature. System will absorb the heat and in the process and use the energy to do work by pushing the piston as I described just now. Okay, so here we can see that during this process, so the state 1 and state 2, okay, we can see that between state 1 and state 2, what are the things that changes? The pressure change. Okay, let's look on the pressure. The volume is definitely changed. Obviously, it goes from 2 liters to 5 liters. But what about the pressure? The pressure must also change because now you are pushing, the piston is pushing with a higher and higher force in order to overcome the gravity. All right, so both P and V changes, all right, but internal energy does not change. That tells you that, okay, only temperature can determine the change in internal energy. Okay, so maybe that one is not very obvious for some of you. If it is, then it's fine. Now, if it's not obvious, let's do a second experiment, right? Second experiment, a free expansion experiment as well. Consider free expansion process in the figure below. So imagine you have an isolated system consisting of a gas, helium gas, inside your flask, and then this helium gas is divided inside the flask. So this is the overall flask. Okay, the helium gas is contained on only 1/2 of the flask, and it is separated by a flexible membrane, like a skin or membrane, to separate it with a vacuum. So the other half of the flask is vacuum. There's no gas, there's no matter. And then surrounding the flask, you have an insulator, an ideal insulator, whereby energy cannot come in and come out. So all the energy is contained inside the gas or the flask. Okay, now what will happen if you break the membrane? So the membrane separating helium gas and vacuum, what will happen if you break it? Once you break the membrane, definitely the helium gas will instantaneously and spontaneously expand and fill all the vacuum region. Almost instantly, the helium will expand instantaneously, fill up all the void of the vacuum, and then the volume has increased, because previously the volume is only one half of the flask. Now the volume is the whole flask. Same initial and final states as in isothermal process, but no heat into or out of system. Insulator isolate the system. When membrane broken, gas will fill the whole container, but does not do any work. But does no work. That is another word, because it is not pushing against anything. So another thing that I need to stress here is that when you have work done, so in order for thermodynamic to have done work or be done work on it, okay, the boundary must change. Either the boundary is being pushed to expand, or part of the wall of the boundary is being pushed out like a piston. So if the boundary does not change, the volume of the boundary does not change, that means there's no work done. There's no physical work done, because work done must be a physical thing. So if you look here, there's nothing physical about you may say that, okay, the helium gas is pushing against the membrane and the volume and the vacuum and all that, but remember, the membrane, you break the membrane, it's not pushing the membrane, it basically go through the membrane, through the hole that you created, and then fill the vacuum. But vacuum is nothingness, so that means helium that is filling the vacuum is pushing against nothingness. So it's not pushing against a boundary, so it does not do any work, although it is expanding, right? So that's why in a spontaneous expansion like this, the system does no work, because it's not pushing against anything. So we call this free expansion. So in this free expansion, you can say that gas fills the flux, but both Q and W are zero, because Q is heat transfer. You have an insulator there, no heat is transferred in and out from the system, right? So Q is zero. W is also zero, no work is done, because we have established that the helium gas is expanding, but it's not pushing against anything, so no work is done. It's a spontaneous thing that happens. That's why if you go up in space, if you have a container that contains gas, if you poke a hole, it's basically just spontaneously expand, and sometimes just explode, right? Because it's just a what we call a free expansion. It's free to expand without any hindrance. It's not pushing or trying to do any work, so no energy is lost, right? So therefore, internal energy, so if Q and W are zero, based on the first law of thermodynamics, we know that first law of thermodynamics is like this. Okay, so if both of these are zero, then this one must be zero as well. The change of internal energy must be zero as well. But the question now, does the T change? Does the temperature change? It can change, for which case the change of internal energy will not become zero anymore. But if T is constant, then internal energy must be constant too, but P and V changes. So we know that the pressure has changed, the volume has changed. The pressure now from here to here is different. Of course, this one will have less pressure because it is now in a bigger volume, and then the volume has also doubled. Okay, but in a free expansion, normally temperature does not change. Temperature will not change. Temperature will change if and only if the container itself is very large. Okay, it's very large, then temperature can change. So imagine if you have, like, if you go back home, right? If you have like a spray can, like a mosquito spray or paint spray, or maybe just a compressed air spray, if you continuously spray it a long time, you will notice that the can will become cold over time, very cold compared to the surrounding temperature. That is because the gas is expanding almost freely. Okay, and then the internal energy will reduce. So when the internal energy inside the gas can reduces, then temperature will be reduced as well. Okay, so if you have a large expansion, or if the helium is expanding very large, not just two times, or maybe it's expanding like 100 times, then only you can have a significant change in temperature. Therefore, from the experiment, we can conclude that internal energy of an ideal gas depends only on its temperature and not on its volume. Okay. For non-ideal gas, the internal energy depends not only on temperature but on pressure as well. In reality, non-ideal gases, when experience free expansion, will also experience drop in temperature, as I mentioned just now. Okay, so lastly, in this section, or in this chapter, we will look at the energy transfer mechanism. Particularly, we are looking at thermal energy transfer mechanism. Okay, so I will not go in detail about this because it's very basic. You all should know this. Okay, energy transfer, thermal energy transfer can happen from one of these three processes, either conduction, convection, or radiation. Conduction is when you have two objects in physical contact, so you are conducting the thermal energy from one object to the other object. Convection is through the movement of fluid. So let's say if you have a pot, and then you fill the pot with water, and then you heat up the bottom of the pot, so the water immediately at the bottom of the pot will become hot, and then it will move by convection to the up, and then the water from the top will go to the bottom and get heated up, so it will cycle that way. So that's convection, similar to the fluid of air in your room. If you have air conditioner, okay, your air conditioner will cool down the immediate air around it, and then the cooler air will move around because of the change of density. Okay, and then it will start to uh, transfer the thermal energy around the room. So convection is due to the fact that gas and fluid will change in density when the temperature change. When there is a temperature change, there will be a change in density, and when you have different density of the same material in the same container, then it will move around. Okay, the third one is radiation. Radiation is by electromagnetic wave. Electromagnetic wave, that means optical. All right, either by visible light, by infrared, by UV light, by radio wave. All right, so anything that is electromagnetic wave is by radiation. An example of radiation transfer mechanism is from the sun to the earth. So thermal energy from the sun, how does it transfer to the earth? How does it happen? Because in between the sun and the earth is vacuum, there's nothingness, right? So we cannot say that there's conduction because there's nothing connecting between the earth and the sun. We cannot say there's convection because there's no liquid or there's no gas between earth and the sun. So the last one is radiation. So electromagnetic wave is being bombarded by light from the sun to the earth, and then that's how thermal energy is transferred. In fact, most of the energy that we have on earth is from the sun due to radiation. So you can read through all of them, okay, and then the relationship between how to measure the power transfer of thermal energy through conduction, and how to measure it through convection and also radiation. No, for convection there's no calculation, radiation there's calculation. Okay, and then for conduction there are several equations. So P here is the power, so how much of energy is being transferred per unit time. Okay, and it depends on the material, on the two There must be a hot and cold. If it's the same temperature, then there's no net heat transfer. There's no net thermal transfer mechanism. So there must be a temperature gradient between the two objects. So that's all. Okay, so that's all today. So you can read more about ideal absorber and blackbody. What do they mean? Okay, so in summary, okay, I just want to point out that the first thing that is important about the first law of thermodynamics is the equation governing the conservation of energy of thermal energy. So you know what is change in internal energy, work done, and also heat transfer, Q, delta, EINT, and W. We have looked at heat, specific heat, and latent heat, important in looking at the change of phase of material and also the change in temperature. Heat and work in thermodynamic processes, first law of thermodynamics, example of thermodynamic processes. That's four. Remember, there must be isovolumetric. What else? And then we have isobaric. And then we have isothermal. And the fourth one is adiabatic. Okay, isovolumetric, volume no change. Isobaric, pressure no change. Isothermal, temperature no change. Adiabatic, no heat transfer. Okay, so that's how you remember it. And then lastly, internal energy of an ideal gas. We look at the experiment in explaining free expansion, and in this experiment it's important to explain that change in internal energy only depends on temperature and not pressure and not volume. So the change in volume and change in pressure does not determine whether there will be a change in internal energy. Only the change in temperature that will cause the change of internal energy. And then energy transfer mechanism. Well, that's all. That's all from me today. Thank you so much. We will continue on Friday. I hope to see you tomorrow, inshallah. Okay. See you again. Assalamualaikum and goodbye.